Well, that was typical. Microsoft microphone was off, so I've been speaking by myself for a while. Very, very nice experience. All right. Sorry about that. Let me start again. All right. What was I saying? So, last time we talked about creating processes and avoiding the creation of zombie processes and so on. So the story of this is that we actually want to have the resources, the hardware resources of our computers used as best as we can. We have many processes, we have processors, we have many cores. We want to use them, right? Since we have them. So to do that, you need to be able to write programs that do multiple things at the same time, basically concurrently. And the first mechanism to do that is creating processes. So if you want to do things faster, maybe you can split that task over multiple processes, and um, those processes will run on different CPUs or maybe on different cores, and things will get done faster. So, how do you create processes using fork? Fork is a mechanism specific to Unix and Linux, and it has a peculiar behavior. As soon as you call fork in your code after the fork will be executed into processes. So the code after this point will exist into processes and it will be executed twice. So practically fork created a child process. The initial process is called parent. The one created by fork, which is a copy of the initial, is going to be called child. In this program, you can differentiate whether the code you're writing will be executed in the parent or the process, relying on the value returned by PID, by fork. Basically, fork returns 0 in the child and returns the PID child in the parent. So, as soon as you run fork, um, the this will be executed into processes. In the parent, PID will not be 0, so the parent will not execute this. In the child, the PID will be 0, so the child will execute this. And that's how we know where we are. You can remember the return value of fork by thinking that the child knows its own PID, but the parent doesn't, so it needs to be given. Hence, fork returns the PID of the child in the parent and 0 in the child. All right? Okay. And then we discussed about uh, zombie processes. So if I am to go over this again, if a parent process creates a child process, it's only natural that the parent would want to know whether the child process finished with success or not. Basically, the parent created the child process so that it executed some computation and it would need some feedback on how that went. Consequently, there is a mechanism for retrieving this information about the child process, and that mechanism is wait. Wait waits for the child process to finish and returns its exit code and a little bit more actually than the exit code. Now we usually called wait 0, but that 0 is actually a null. We should pass a pointer there. So if you scroll in the documentation somewhere here, let's see, maybe up. Give me a second to find it. Well, maybe down. Here. So if you want to get the return value, the exit code of the child, you could call wait with a pointer to int, right? Status is an int. And then you can get from that status the actual exit code using this kind of call. So the exit code is normally a byte, 0 to 55. You're passing a pointer to an int, which is 4 bytes, so that int will contain a bit more information. But if you just want the exit code, that's how you fetch it. So this is just so that you know that wait is not always wait 0. It can take a pointer and it can bring you some information. But coming back to what I was saying, the point of wait is that it tells the parent process, the exit code, the status of the child's functioning. Now, because the parent must have this information, the system, even if the child stops the execution, finishes the execution, the system will keep the child as a process, as a weird process that doesn't execute anything anymore. So it's basically just a record in the system's list of processes. It's just a record. Basically, it exists, but it doesn't execute. It's dead, but it still exists, hence zombie. So this zombie will exist until the parent calls wait. As soon as the parent received the information about the child's execution, meaning exit code and a little more, the zombie is removed from the system. So I just want to show you how this works. I want you to be able to see zombie processes, and then we'll discuss a few situations where they will be problematic and how to solve it. Now, any process will exist as a zombie for like a microsecond, right? Just in between calling exit and then the parent calling wait. Even if that happens right away, there will be possibly a very short state of zombie, right? The problem is if the state of zombie extends for a long while, and then the number of zombies accumulate, and then you end up with a system where you don't have any more process IDs available because they are all taken by zombies. Hence, you cannot create new processes. Basically, the system will be stuck. So for now, let's have a look at this code. And I will need to make a few fixes here, just so that we have enough time to discuss it. So I'll copy this in a C file. Let's call it vi zombie. Right? Okay. And what this does is really simple. It's a little program that creates a child process. The child process sleeps for 10 seconds. The parent process, which does not execute this piece, sleeps for 15 seconds and only then calls wait. So then we will have 10 seconds of seeing both processes and then 5 more seconds in which we will see both processes, but the child will be a zombie. Then the parent calls wait, so after second 15 the zombie is gone, and then the parent stays 5 more seconds and then it stops as well. Now in order to see this happening, we need we need a little script that shows all my processes continuously. So here is the little script. It's just a simple while true, and it just displays my processes in the system. It clears the screen, displays the processes, sits for a second, and then clears the screen, and so on. So if I started, this is what I see, right? So I see the VI that I have in the other session. I see the PS, which displays this actual information, and I see my two sessions, the SSH and the bashes. So I will improve this a little bit so that I don't see all these other things which are not really interesting. So let's just grab -v, anything that has to do with SSHD or bash or vim or ps-f-u. All right. So for now, this is it's if you want, it's a monitor of the current processes that keeps refreshing every second. So now let's get out of here and compile it. You'll see the GCC coming up underneath, probably. Oh, they didn't quite catch it because GCC was really fast. So now I'm gonna run zombie. So remember, 10 seconds, both processes, parent and child. 5 seconds, parent still running, child zombie. Then the zombie stops, parent runs 5 more seconds. So here we go. Zombie. And on the top is the parent, and you can see that its ID is identical to the parent ID of the child. Now, anytime now the child will finish, it did, and you see it as defunct. This is a zombie process. And now the parent called wait, and then the parent lives a little longer, and it stops. So let's do this again. So please watch carefully. I'm not really sure how great this is happening in the stream because the screen keeps flashing, but probably it's not so bad. I could try to, but it will probably flicker if I remove the. Okay, you can see it well. If I remove the sleep, nah, not very good. Without the sleep, I don't see much. So we need the sleep. All right, so here we go again. So parent and child. Parent is at the top. Any second now that the child will finish execution, but the parent will not call wait for 5 more seconds. So we have 5 seconds of zombie. This is what calls it zombie. Now the parent called wait, zombie is gone, and in a minute, yeah, in a second actually, the parent gone. So this is zombie viewing, not as exceptional experience as you might have expected, but still, those are zombie processes. So the problem with zombie processes is not that they exist, is that they may exist for a long time. Because that zombie process did nothing but it occupied the process ID. So I need to make sure my zombie processes are short-lived or else my system will get stuck in time. So let's look at the situation where this becomes very obviously problematic. This is seminar stuff here. So one situation where zombies are problematic is when we are dealing with servers. Now, I'm going to show you, if you want, a skeleton of a server that does things concurrently. Not this is possibly the least performant server, but it's a start. You'll learn later how to do things better. So let's go like this. A server is a thing that serves requests. For instance, Google has a server for searching, right? And you go to Google and you say search for cat, and Google will reply. Now, it's pretty obvious that Google does not serve each request sequentially, meaning, oh, you asked for cat, let me give you the results, and then I'll look at whomever is asking for anything else to search. If that would happen, every search would take a few days. We have a question. When a process becomes a zombie process, is it always shown between? Well, probably. Yes, probably. It really depends on how PS is implemented. You can check, maybe it will have another, you can influence this display somehow, but mostly yes. The defunct word is probably the best detector, but if you go on another system, not a Linux, it will probably be different. So now coming back to servers. So a server will need to serve requests concurrently. Otherwise, you'd have users waiting for previous users to be served. And this is not going to make your server very popular. So you need to do things concurrently. So how do you do that? Especially that you have many cores, many processors probably. So this is a skeleton of a server, right? Let me zoom in a little bit. So you can think of a server, the core of a server, to be this while loop, all right? For now, ignore the wait part. So you would have an infinite loop, which is normal because the server will run for a long time and it will just be stopped from outside. So there is no stopping condition for a server. And what will it do? It will say get a request. Request may be something like search for cat, right? and then create a child process, and then in the child process, handle the request, meaning get the results, and send the results back to whomever requested them, and then stop the child process. Right? So ignoring the wait, what will this do? A request comes, parent process gets it, creates a child process handles the request. In the meanwhile, the parent goes and gets another request and creates another child process and another child process. So if you have 300 people sending requests to your server, you'll spawn 300 processes, each of them handling one of those requests. Okay? Because the parent does not need to wait for the child process to finish handling the request. That's happening in a separate process, and the parent can get back to reading another request. This is the whole trick. If this is not clear, please ask. Now the problem, and this is just a small parenthesis, I told you this is not very performant, and it's not. If you have 300 people sending requests and you spawn 300 processes, that may overload your system. There are better, lighter ways of handling things concurrently. Processes are not exactly that light, but the principle is pretty much the same, regardless of what technology you use, be it process or thread or anything else. So the parenthesis was, this is a server skeleton, but it is not a performance server skeleton. If you're into finding about that stuff, please search the web for something like C10K or even C10M, and you'll learn about this a lot more. C10K handles the question, how can I write a server that can handle 10,000 requests per second? And C10M is looking at 10 million requests per second, but the architecture in the second case is going to be completely different. So for now, this is just a pointer. So let's stay with this case because our goal is to understand deeper how fork and wait work. So in a situation like this, I have a server that serves things concurrently. The problem is this server never ends. And if this server never ends and does not call wait, its zombies will live forever, waiting for that wait to be called. So the question is, where do I call wait? If I call wait here, suddenly my code is sequential again, because the server will not be able to go back to getting a request until the current request is served by the child. So putting a wait here really kills the whole purpose and makes it even slower than just having a regular sequential flow with no fork. So wait here is not a good thing. If you put wait here, right? Wait, well, you never get here because it's an infinite loop. So practically, you don't really have any good way of calling wait, which means that if your server is really popular, in a matter of minutes, maybe hours, your computer will be full of zombies and you'll have no possibility of serving any further requests because you cannot create more processes. If you call wait here, then it's gonna be sequential and slow. So how do we solve this? And I would like you to think about it for a few minutes or seconds and suggest a few approaches here in the chat if you get any ideas. They will probably not be the right ones, but it's worth discussing them and understanding why not. Okay, so let's see. All right, now, so we have Void Boy Wannabe suggesting that we should change while one to while get request. Not a good idea because that means that as soon as I don't get a request, my server stops. which is not a right. The point is for the server to live and serve requests whenever they are available. So no, that will not do the trick. I will need to keep waiting for requests even if they're not coming. All right. What if we just count the requests and when we reach a certain point we call wait? Yes, this is a possibility and its problems are a little subtle. Let me see what else other people said. Have a process that monitors processes and kills defunct processes. You could do that too. Child processes that wait for requests and the parent process, pretty much the same idea. Call wait only when a request has been handled. So I'll address this. When you say call wait only when a request has been handled, how do I know? So this is William Cadeth. How do I know that a request has been handled so that I only call wait at that moment? This is the actual solution that I will show you, but I haven't told you a mechanism yet that gives you the information the request has been handled. With a flag, okay, using signals. Thank you, Berzent. Signals is where we're going. But flag, William, I'm not really sure how that flag would work. All right, so I have a question from T-Flag, and which this is important to clarify. You don't understand why the child process isn't killed when exit 0 is called. So let me clarify this. Exit, you see, zombie is the state between death and being alive. Exit kills the process, but kills the execution of the child process. But every process has a record in the list of processes of the system. And you see that when you run PS and you see the process in the system, you're actually looking at the table of processes. So even though the process stopped executing, its record in the list of processes is kept. Hence, it exists, but is dead. Hence, it's a zombie. So exit 0 controls the finishing of the process's execution, but it does not control the disappearance of its record from the system process table. That is controlled by the wait of the parent. Because the record in the system process table carries with it the exit code of the child process. And when the parent calls wait, it gets that information from the system process table, and then that record is cleared. Have I made this better, tflag01? All right, cool. So let's see what else. Now William is thinking with a return code which is actually a signal. So basically, a signal is not a return code. You cannot really use here return codes because how would you return a value from a process to another process? If I am to put it differently, how do I return a value from VI to grep? Right? It's not something that you can do. I have here a few suggestions above. Let's see. Kind of getting lost in this. But basically, there were two suggestions. Have another process that monitors zombies and kills them. Well, zombie killing would work. In the older days, you couldn't really kill a zombie. You know, even in the stories, you need like a silver thing or something to kill a zombie. You just couldn't kill a zombie. The only way to kill a zombie would be for the parent to call wait. Hence, another process couldn't do much, right? But nowadays, I believe you can. But even so, If you're running an extremely popular server, you may have thousands of requests upon thousands of requests, and it may still fill up your process table before the other process can clear it out. So we have a better solution for that. Another suggestion was maybe I think that what the suggestion was that, well, maybe let's say every 100 forks we could stop and wait, right? So we do 100 requests and then we wait for their zombies and then we do another 100 requests. So this would work, but if among those 100 requests there is a really slow one, you'll practically interrupt the execution of your server until that's done. So your server will execute with hiccups, which again will make it less popular. So even this is not so great. Okay, so Rareshika 4321, what's the advantage of using processes over threads? That's an exam question, really, but I'll answer it. Threads are more lightweight, but if you have an error in a thread, you have like a segmentation error or something, segmentation fault in a thread, the whole process dies, right? If you have an error in your code and the child process dies, the other processes continue executing. So this would be an advantage. So even I haven't checked in the recently, but try and catch the whole thread. Do that in C. Do you have exceptions in C? Can you catch a segmentation fault? I don't think so. And even so, have a process monitor to see the status and stop them if they're dead. Well, I think we've discussed that already. Now, for instance, the Apache server, which is an HTTP server, it creates a number of worker processes, and then each worker process creates threads. So they have this approach that it's a mix of processes and threads. Threads probably handling things much faster, but if something goes bad and a thread crashes, then you still have other worker processes still working. I'm thinking. I don't know the actual reasons for their decision. Okay, so this was long enough. Let's go and look at the solution. Okay, is there a fork? Well, C++ can call C functions. What you're asking for is there a fork implementation that throws an exception so that you can catch it? I don't think so. You may try to implement one. Mortuary, I don't know. Actually, I don't know. I don't know the answer to your question. So let's move on to the solution to my question. How do we wait for child process in this situation? And the solution relies on signals. So I will start with an introduction to signals. And those of you who had seminar with me have seen this already, but I will have to show it for everybody, so you'll see it again. So the first question is, what's a signal? And the simple answer is a signal is an interrupt. Now this would have been enough for you a few years back, but now as you're not studying interrupts in the assembly class, I will need to go through that too. You can think of an interrupt as a process, or sorry, as a process being poked with a number. So think of it as you are a process and then you get tapped on the shoulder. If you get tapped once, that means there was a division by 0. If you get tapped twice, that means somebody wants to stop your execution. And so on. So Signals, interrupts, are the most basic mechanism for communicating between processes. It's a simple poke, and the only information that they carry is their number. That's it. Now, there are interrupts at hardware level and at software level. Indeed, if you get tapped 9 times, that's kill-9, and that's the ultimate killer. Yes, we'll get to that as well. So an interrupt is a mechanism that interrupts temporarily the execution of the process, and in that interruption, the process executes a function which is associated with the interrupt. So basically, if you get tapped 17 times, then you have to execute the handler function corresponding to the signal 17, right? Now, several of these handler functions simply exit the process, but others do other things. So let's have a look at this. For instance, if I run the program cat, right? Just like this. Now cat is stuck waiting for user input. If I want to stop it, I can just hit Control C. This is actually sending it an interrupt. The interrupt is called SIGINT, and the handler for this interrupt simply exits the process, right? So let's have a look at at the many ways in which we can kill a cat. So we start the cat, and then you've seen the Control C version, but from this other window we can find its ID, its PID, right? So the PID of this process is here. So I can just say kill -2 and the PID, and it stopped. So basically Control C issues signal number 2, which is called SIGINT, to the process, and the process calls the handler for signal 2, and the handler, the default handler, is just exit. Let's have a look at what signals do we have in the system. 7 signal in section 7. So down in this manual page, here you go. So let's see what we've got. SIGINT, signal number 2, interrupt from keyboard. This is Control C, all right? SIGHUP, signal number 1. SIGHUP is actually hang up. When you close your PuTTY from the little X button there, all the processes running in that session will get a SIGHUP. By default, the handler for SIGHUP is exit, so they will exit. That's why if you close that PuTTY window while VI is running, VI will stop and leave behind all these files that then they will give you trouble. Okay. We also have SIGTERM, signal 15, which also is another way of stopping a process, and we have SIGKILL, which is value 9, which also kills processes. And there are a bunch of signals here. Okay, so let's play a little bit with them. Let's start cat again. Let's find its PID, but maybe we get a little crafty and we say grep cat at the end of the line, right? And then just awk print $2. So this is the PID of the cat, all right? And then we can just say kill dash sig term, right? So this will kill the cat with sig term. And now it says terminated, right? We can do the same with sig kill. All right, this is not so great. How do I get rid of this? Uh, this is a bug in Bash terminal handling, which I dislike, but here you go. If I make it smaller, it got better. So if we put here sig kill, then the cat is killed, right? It's not a real cat. I actually love cats. Because I see you talking about this. Right? Kill dash 9 is the same trick as sig kill. So I told you at the points kill dash 9 is the ultimate killer. That's you'll get the idea about this. Why not use Tmax? This is a side question. I'm not going to go into it for now. Yes, you can use Tmax as well. So the trick about signals is that you can change the handler function for them. So let's just do a little program that refuses to stop when you hit Control C, and we'll call it no. All right, so this is it. Let's compile it. And when we run it and we hit Control C, it doesn't stop. So what does this do? So let's look at how we play with the signals handler. The program is really small. It only cycles forever, so it does not do anything special. But before starting doing that, we register the handler function f to be called when SIGINT is received. So this is a source of confusion for all students. Signal does not signal anything. Signal just registers a handler for a certain signal. Kill is the function that signals. There is a command kill and then there is a function kill. So kill sends a signal, signal only registers a handle. So a handler. So what is the handler function? It's a very simple function. It must return void and it must receive an int, which will be the signal number, and then it does something. If this something doesn't do exit, then it will not exit. So every time we give it a Control C, it will print out, and that's it. So I'm going to need to stop this function somehow. So there are many ways of doing it. I can find its PID from here and use another signal to kill it. Another thing that I can do is hit Control Z, which sends it to the background. PS, find its PID, kill dash 9, this guy. And now it's over. And it tells me it's been killed. Okay, so this is a way of stopping it. So let's improve this a little bit. Let's do something like this. If SGN is 2, then, and now we'll go to something that relates to the virus. I am immune to SIGINT. Actually, let's call this Control C because it's easier to understand, right? And this is a JavaScript equal, which we don't really need here. Else, if SGN is 15, then it will say something like I'm immune to SIGTERM, right? And then if the signal is 9, it's gonna ask itself, am I immune to sig kill? Right? So now we have a handler that can deal with that does different things for different signals. And now we just need to register it. So let's register it. For SIGINT, it was already registered. For SIGTERM again, and then for SIGKILL. Oops, something went wrong here. I'm not really sure what's going on. All right. Okay, so I have a handler and I register it for 3 signals, and it will do different things for different signals. So let's compile and run. And now we run it. Control C. I'm immune. Control C. Great. Now let's find its PID and kill -15 this guy, and it will say I'm immune to SIGTERM, right? But then if I do kill -9, it just stops. So SIGKILL cannot be overwritten. So the handler of SIGKILL cannot be overwritten. Although we register F as a handler for SIGKILL, this is ignored. And SIGKILL will always kill the process. All right, so this is how signals work. And here is why I went through all this thing in relation to processes and fork and wait. Because there is this one signal which the child sends to the parent whenever it stops. So practically, whomever suggested above that we would need to call wait only the request was serviced. The question was, how do we know when the request was serviced? And this is how we know. When the child process finishes, it sends a sick child to the parent automatically. So then we can write this kind of code to solve our problem. If you look at this, you'll see that the while loop is identical to what's above. It's a never-ending loop in which we get the request, we fork a child process, we handle the request, we send the response, and we exit. But there is no wait here. However, before we enter this infinite loop, we register function f to be called whenever sick child is received. And all we do is do a wait. So with this implementation, we will never have long-living zombies. As soon as a child process is finished, it will send us the sick child signal, and we just call wait for that, and we're done. A simpler way of doing this is not even having a handler, but just ignoring. So with signal, we register that sick child is going to be ignored. And this means, this is like saying, if the process child is finished, I'm not interested in it. So then the system will clean out the zombie for us. All right. I would like to know whether you guys have questions about this. Otherwise, I'll go into another story, which is a little more complicated. Storytelling. Yes, storytelling. Everything is storytelling in a way. So the basic idea is to register the sick child and handle it with our own handler as we want. Exactly. Knowing that every child process ending will be causing a sick child to be sent to the parent, we instrument the parent with this handler for sick child, and the handler just calls wait. Or simpler, we simply configure the parent to ignore SIGCHILD. And then whenever the child finishes, since the parent ignores its exit code, the zombie can be cleared. No, I think it has an empty handler. Nothing happens really. So whenever SIGCHILD is received, it's calling a blank function without anything in it. And we're practically replacing it with a function that calls wait. This is mostly an answer based on my intuition. I haven't really seen the code, but we can dig for it and see exactly what it does. The actual code is most likely more complicated. What I'm giving you here is, let's say, the idea of how things work. But when you get to the implementation, things will always be more complex. Can we return from a child any value that is larger than a byte? Not really. No. If you want to get from the child some data, then we'll need to use pipes, and that's next week. So if we really want to transfer data between processes, we need different mechanisms. All right. So for now, we are good with creating child processes that know how to execute uh, different code than the parent. We know how to wait for them so that they don't become long-lived zombies and fill up our table of processes. But still, it would be really good if we could be running another program from our program. And this is where we're going now. If I have, let's say, thousands of files to be encrypted, it would be lovely to, and I have a program that knows how to encrypt a file, it would be lovely to be able to write a program that simply runs the encryption program in 100 copies, and then I will be encrypting 100 files at once, instead of just doing them one by one. So the question that we're looking at now is, how are we going to run a program from another program? So let's see here, we have something from Teradict. Is there any reason why we shouldn't do wait on every SIGCHILD? No, I don't think so. You can do that, yes. But, well, there is a reason. If you're interested in the exit code of the child, this will hide it for you, right? This just discards it, and this as well. So if you are interested in the exit code of the child, then you should handle it as you need to. This is just simply saying, I don't care, I just want zombies to be gone. So here we go, the next piece. Trying to make this a little wider, but no. Okay, now it looks right. Okay, so we're getting to the point where we want to run a program from another program. And for that, we have a set of exec functions, a number of them, and they have, let's say, formal differences, but the function is pretty much the same. So you can do man3 exec, and you get the functions. And here is how they differ. I will ignore this one with the E. I don't care for it, but you can read about it. The ones that we will probably care for are the other ones. So here is how they differ. There are two criteria: whether they search the path for the program that you want to run, and whether the arguments are passed as a list or as an array. So let's see this one. Every exec that has a P at the end suggests that the function will search the path for your program. So let me go through the path. I've explained this to you probably before, but I'll show it again. When I run ls, right? How does the system know where the program ls is on disk? Right? Or if I run GCC, how does it know where it is? So the trick is an environment variable named path, which contains, one second, let me see, which contains a list of directories in which the executables are searched for. So if I run ls, what it will do is look in this directory. Is there an ls? No. Okay. Next one. Is there an ls here? No. Okay. Is there an ls here? No. Is there one here? No. Is there one here? Yes. And then that's the one that gets executed. So if you just say ls, the bash will practically go through this path and then run the first ls that it finds. There may be several. So this is what this function does. You can just say grep and it will search the path for grep, and the first one that it finds, it executes. If you don't have it in the path, it will fail. These other ones, without a p at the end, will not search the path. So you have to give them the full path to your executable. You see that? Or here. And then there is the difference on the horizontal dimension of how the parameters are passed. So if you know exactly what parameters to give, you can just pass them like this really nicely and put a null at the end, meaning you know how many arguments you have and what they are. Same here. But if you don't, you can do it dynamically. You can put all the arguments in an array that ends in null and you just pass the array. But it's the same thing, just it's a different way of passing arguments. That's all. All right, so let's do a little program to see how things work. So I'm going to take this piece of code. And I'm going to replace this quote because it's a word quote that will not really compile. Okay. So what this code does, well, it pretty much, the program will run the command grep and it will extract all the students from group 211 from the file password. Now this will result in a lot of output, so I'm going to change it to just display my entry in etc password. Okay, so let's compile this. All right, and now when we run it, we get my entry in an etc password. Now we need to look at this closely because there is something not quite clear here. There are probably two questions to be asked. Why a second grep? Or three, why a null? And why isn't this being displayed down here? So here we go. The first grep is the command to be executed, just like it's here, or here, or here. The second grep is actually argument number 0 of our program, which is the name of the program. If you recall, $0 is always the name of the program. So we need to pass that explicitly. That's why there are two greps. So even here, you can see it's doubled. Same here. And here, where you pass the arguments as an array, the first element in the array is still the name of the command. Okay. Yes, the null at the end is to mark the end of the argument. Yes, you see, in C, arrays don't really carry a length with them. So if you pass to someone an array, you need to also tell it where it ends. So you either give it a length or you put a marker at the end. In this case, the choice is placing a marker at the end, and that means a null. Okay, what if the argument 0 is different than the name of the process? I believe there is no problem. You will simply be telling the process that it's called something else than it really is. Uh, you can actually make a little test with this, write a program that prints out its 0 argument and then call it from another with exec and give it some other name, see what happens. It should not be any big issue. So we clarified the duplication of the command here and the ending null. But the question is, why is this not printed out? Because it's not. And this is where you may read here this unexpected behavior. Exec has a sort of parasitic behavior. You have a program that calls exec. So when you run that program, it becomes a process in memory. And the process executes, and at the point it reaches exec, exec needs to run, in this case, grep. But it does not create a process for grep. It simply reuses the current process, empties it of its code, and populates it with the code of grep, and then starts executing from the first instruction. So it's like exec takes over the current process, empties it, and puts another brain in it.